Okay, hello, welcome. This is now question number 2 for the AQA AS Physics. This is Unit 1, January 2009. Okay, so it's quite a long question. It's worth a good 13 marks, okay, and it kicks off with a 6-mark written question. Now, again, I do state with all these questions, you can answer simply in bullet points. You don't have to go through the whole process of going, oh, for God's sake, I've got to write a whole essay because they've given me a page. It's not English or economics or history or anything like that where it's crap and you have to write a load of words. Again, it's just bullet points. And the question is asking about, it says, when light of a certain frequency is shone on a metal surface, electrons are emitted with a range of kinetic energies. So quite clearly it's relating to the photoelectric effect. And it gives you, it will always give you a bit of a guidance on what to include in your answer. Okay, so in this one it talks about, explain in terms of photons why electrons are released from the metal surface and why the range of the kinetic energy, why the kinetic energy of the electrons that are emitted varies up into a maximum value. Okay, so as long as we explain them 2 points very clearly, okay, and obviously don't make any mistakes with our writing, we should be absolutely fine. Okay, so what I'm going to do is write down the key points you should talk about and give you a bit of a guidance onto how it's meant to answer the question. Now, on the mark scheme, it always gives a lot of writing to say it's this is what a level 1, level 2, etc, etc. The point being is it will give you a couple of bullet points at the end, which I'm going to go through and explain why they put them there. Okay, but generally it's about knowing that you all the writings before that is just saying, you know, how many bullet points of these do they include, etc, etc. Okay, so as it says, the first thing we need to talk about is why photons are released from the metal surface. Okay, so basically we need to explain how they are emitted. Okay, so one of the first, well, you need to mention, sorry, one sec. Yeah, you need to say how they are released, okay, and what kind of constraints there are surrounding that. And it might be a good idea just to have the formula book open with you about the photoelectric effect. So the kinetic energy equation is a good one to relate to. Okay, so the first point you would say is that the photons, or a better way probably would be saying the instant photons, arrive at the metal surface and transfer their energy. Okay, so transfer energy to the electrons in the surface of the metal, to the electrons. Okay, so, but obviously you need to also specify that the electrons, not every single frequency, sorry, not every energy of photon will emit an electron from the surface of this metal. Okay, you have to therefore talk about the work function and the overcoming that. Okay, so as it says, one of the points I mentioned here is that the energy of the photon is equal to E is equal to HF. Okay, so that's the next. You could maybe mention that as your next point. You don't necessarily have to. Okay, so you say the energy. So you put next point. You might be about the energy transfer. So the energy from one photon is transferred to one electron, and therefore you could also state that the energy of a photon is equal to E is equal to HF. So basically, you need to really, in the next point, talk about the fact that the energy that the photon actually physically transfers is equal to HF. Okay, and you might want to state what the individual parts of the equation are to do with as well. Okay, so then you might want to talk about the kinetic energy equation. Okay, so in other words, we would talk about the fact that the point I was mentioning about not every single energy of photon will emit an electron from the surface of the metal. Okay, so the point you would talk about there is the fact that HF, or the energy of a photon in other words, has to be bigger than the work function, okay, bigger or equal to, the work function for electrons to emitted. And obviously, okay, so apart from my crap writing there, you can kind of make out that because my camera's pretty good now. Okay, so that's what we talk about, and obviously the next point after this, or you could link it into the same point, you would bring in the kinetic energy equation. Okay, so your kinetic energy equation, you would say the kinetic energy of an electron, or the maximum kinetic energy, is equal to hf take the work function. Okay, in other words, the energy of a photon minus the work function, or you could say that any energy left over when the electron overcomes the work function is going to be transferred as kinetic energy. Okay, so really you could link it in from this point. You could say therefore, as this, remember this shows a maximum value, and the next point it asks us to explain is why the kinetic energy of the electron varies up to a maximum. Now, as I say, you don't need to draw any diagrams for this, but I will just draw one diagram. Okay, so say this is the surface of the metal. We've got obviously electrons here, and obviously as we go lower down, we've still got more electrons, and obviously they're arranged something like this. Okay, and obviously these electrons here, when they receive, all electrons will receive exactly the same amount of energy. It doesn't matter if they're all the way down here or if they're at the surface. And this is a maximum, okay, because this is assuming we're talking about the electrons at the surface of the metal. In other words, they don't have to do work to get to the surface. But these electrons at the bottom have to use some of the energy they're given from the photons to get to the surface of the metal, which obviously the ones at the surface of the metal don't have to do because they're already there. Okay, so therefore these will have already lost some energy even before they have to overcome the work function. So quite clearly they're going to have less left over, if any at all, to be contributed to the kinetic energy. Okay, so basically all of that wordy crap was just to tell you that they range up to a maximum because the electrons lower down in the surface of the metal actually have to do work to get to the surface of the metal to be emitted. Okay, so therefore they have lower energy left over to after overcoming the work function to contribute to kinetic energy. So therefore the electrons further down within the metal, or however you want to word it, have less kinetic energy. Now you can probably condense that into a couple of sentences, to be honest. And maybe you don't need to include every single one of these points, just a majority of them. And now, as I say, obviously this is just a case of looking at the mark scheme, really, and I've tried to go through a couple of points just that I think if you included all of them, and if you spelled everything right, you would get the full 6 marks. Now, generally speaking, about 2 of those marks is attributed to the actual quality written communication. So by doing that method, you only need about 4. You only need 4 points, really. Okay, and the rest of that explanation. Okay, if you go on, obviously, if you go on the mark scheme, just mentioned about you've been able to distinguish the fact that there are light consists of photons that equals hf, and they have to be greater than the work function to overcome, and any energy left over will be attributed to the kinetic energy. And obviously kinetic energy at the surface of the metal is going to be greater than kinetic energy at the bottom. So maybe you don't need to quote this equation so much if you're going to explain it in words, but it's up to you. I think it's always nice to include an equation. It doesn't take that long to write, but if you're lazy like me, then maybe you won't. But as I say, it's your life to waste. Okay, so that's the bit of question A out of the way. We've still got, as I say, this is quite a long question, so we've still got part B and stuff to go through now. Okay, so the next part actually gives us a bit of a graph. Okay, so quickly rub this off. Sorry about this. Okay, so as I say, it gives us this graph where we've got the maximum kinetic energy on the y-axis, so I just write Ke, but that's maximum, and we've got the frequency, obviously in hertz, on the x-axis, and it's given us a line which is something like this, where the intercept is some point along the x-axis, and but we've got a constant gradient. Now, before we start going into the bits of the questions, okay, and obviously we're going to have to mark on this graph, as we're told. Okay, this is 2b. I just want to bring your attention. Now, what we generally speaking, when we have, obviously always, this is always the case in AS physics. Obviously, as you start to move into A2 physics, we start to get a bit more, our graphs start to become a bit more challenging, in the words of, we begin to deal with exponential graphs in terms of radioactive decay. But for how you're considering AS, you'll only ever see linear relationships. Okay, so whenever you would see a graph, it's always going to have the form y equals mx plus c, where obviously all of them have their standard values like you would see in core 1. Okay, now y will always relate to whatever's on the y-axis, so in this case it's the kinetic energy. Okay, the gradient m will obviously always represent the gradient, x will always represent something on the x-axis, okay, and c will always represent the y-intercept. But because it's talking about maximum, before I start filling in the rest of those values, you should immediately spot that the equation it's going to be using here is the maximum kinetic energy equation, which is Ke equals hf take the work function. Okay, and you can relate that quite clearly to this graph here, to this equation of a line. Okay, where obviously the gradient is the Planck's constant, frequency is on the x-axis, and the work function is the plus c. Even though it's minus c, still theoretically should work, because obviously c can be minus, and the reason you'd expect c to be minus, obviously, because the y-intercept, if we get this graph going, it'd be a negative kinetic energy somewhere over here. Okay, but as it's not shown as that part of the graph, so don't be put off by the fact you've apparently got a negative y-intercept here. That should make sense, really, because obviously the y-intercept isn't going to happen until we start getting negative kinetic energy values. Okay, so what's going to essentially happen here? Well, hopefully I've explained bits of the graph. Now, generally speaking, in AS and AT really, they will ask what is represented by the intercept, the gradient, that kind of thing. Okay, so the first part, B part, one asks, mark on the graph the threshold frequency, okay, and label it F0. Okay, now the threshold frequency is the minimum frequency for any kinetic energy. Basically it's the minimum, because we know the energy of a photon depends on E equals hf. The threshold frequency is the minimum minimum frequency to allow the electron to be emitted. In other words, minimum energy, and it's a frequency we associate with that. So hf 0, okay, is equal to the work function. In other words, because of this kinetic energy equation. Okay, we assume kinetic energy to be 0, as it's literally just emitted. So therefore, the hf, the energy of the photon, equals the work function, and we call this frequency the threshold frequency. And that's kind of obviously playing on your mind that you need to be aware of that. So basically, if we've got no kinetic energy when this occurs, and the hf is equal to the work function, okay, what we've got here is it's basically just the x-intercept, and that is FO. And it's not coded message, it's F subscript O. Okay, so anyway, that's B part 1. B part 2, on the graph, draw a line for a metal which has a higher threshold frequency. Now, obviously, one thing needs to be stated straight away here. It's going to have a similar kind of, it's obviously going to, because we know the gradient is Planck's constant, it's going to have the same gradient, okay? But if it has a higher threshold frequency, well, the threshold frequency is represented by the x-intercept. It's going to have a higher x-intercept. In other words, the x-intercept is going to be more to the right, but it's going to have the same gradient, so it might look something like this, okay? Whereas the same gradient, parallel line, okay, but it's got a higher x-intercept, okay? Hopefully that makes a bit of sense. Now, obviously, if you'd have said that what's represented by the threshold frequency is for the gradient for some bizarre reason, because you're crazy, okay, and you related that to your part B, you do get an error carried forward, so don't be put off by that, okay? So that's pretty much it, but as I say, hopefully you didn't get that wrong, and I've explained that in a good enough way for you. Alright, so state what is represented by the gradient in this graph. Well, I've kind of already mentioned it, and I've explained why, so hopefully it's not no problems. So that's Planck's constant, obviously. And just to go over that again, because, you know, I like wasting my time. Planck's constant, the reason it's Planck's constant is because the equation, obviously y is equal to mx plus c, and the y-axis we've got the kinetic energy, and the only equation we have maximum kinetic energy, well, it does say maximum, I just wrote kinetic energy because, you know, I'm lazy and I can. The kinetic energy equation is equal to hf, take the work function, where hf is the same as saying mx, okay, so the gradient therefore, because x on the x-axis we've got frequency, the gradient must be Planck's constant. Okay. 2c, so this is the last part of question 2. The threshold frequency of a particular metal surface is 5.6. So f0 for this particular metal, okay, is 5.6 times 10 to the minus 10 to the 14 hertz. Okay. Calculate the maximum kinetic energy of the emitted electrons if the frequency of light striking the metal surface is double the threshold frequency. So they wouldn't have told us the threshold frequency for no reason. We have to actually use it in 2 cases here. Now, it wants us to work out the maximum kinetic energy, so let's just write that equation down. We'll write it over here anyway. So the kinetic energy is equal to hf take the work function. Now it's very good telling us that the new frequency is double the threshold frequency. Okay, well you would just say, well we'll just double the threshold frequency and then sub it into k equals hf. But k equals hf take the work function. We've not been told the work function. It's crucial therefore to know this relationship, that the hf naught, in other words the threshold frequency is the minimum frequency for an electron to be emitted from the surface of the metal. In other words, it would have no kinetic energy. So relating to this equation, okay, putting f naught to be the frequency, we therefore get hf naught to be the work function. And that will allow us obviously to work out the work function we've not currently been given. Okay, so hf, h times the work function, and obviously you know h is given in your formula sheet anyway. Sorry. It's 6.63 times 10 to the minus 34, and that's times the frequency f0, 5.6 times 10 to the 14 hertz, and that is equal to the work function. Okay, which is, according to this, 3.7. And obviously, give rounded error. Sorry, 3.71 times 10 to the minus 19 joules. Okay, so that's the answer to the work function. Okay, and then obviously you would just double this. Okay, so you just times that by 2 and sub it into the frequency. Okay, so therefore you get kinetic energy is equal to 6.63 times 100 times 10 to the minus 34 times 2 lots of the 2 f0, take the work function, which we know is this 3.71 times 10 to the minus 19 joules. Okay, and then you would get your answer of 3. Yeah. I mean, you could just theoretically say, obviously this is going to come to, sorry, because we know that the threshold frequency is going to be double the frequency, okay, of the work function. Sorry, yeah, threshold frequency, the frequency we're using here is going to be double the threshold frequency, and we know the work function is equal to h times the threshold frequency, and this is h times 2 times the threshold frequency. Okay, you could just say it's 2 times that, take 1 times that, which is essentially what all this says, so therefore it's just simply 3.7 times 10 to the minus 19. Okay, but as I say, you would probably do that calculation, that's probably what you need to get the full marks. Okay, so that's the end of question 2C. Thanks for watching, hopefully it's been helpful, and as always, any questions or anything, please do comment below. Obviously, you know, it only pisses me off when people point down there. What the hell is down there? It's actually a bed. But anyway, thanks for watching, and we'll see you in the next video.